The price of anarchy of selfish routing, non-atomic selfish routing, the price of anarchy. This section gives an essentially complete analysis of the price of anarchy in non-atomic selfish routing games. As we know from the nonlinear variant of P-Gauss example 18.3, the price of anarchy depends on non-linearity of the network cost functions. Our goal is to show that it depends on nothing else, not the network size, the network structure, nor the number of commodities. More precisely, we show that for every conceivable restriction on the cost functions of the network, the price of anarchy is maximized over all multi-commodity networks by the network that best simulates P-Gauss example and its nonlinear variants. As an aside, we know that the potential function characterization of non-atomic equilibrium flows, proposition 18.11, already gives a good, but not optimal, upper bounds on the price of anarchy. The intuitive explanation is simple. If equilibrium flows exactly optimize a potential function, that is a good approximation of the objective function, then they should also be approximately optimal. Theorem 18.16 Potential function upper bound. Let GRC be a non-atomic instance, and suppose that x times c of x is less than or equals to gamma times the integrations. Integrate with index from 0 to x of the term c e of y dy for all e in the H set E and x which is greater than or equals to 0, then the price of anarchy of GRC is at most gamma. Proof. Let f and f star be equilibrium and optimal flows for GRC respectively. Since cost functions are non-decreasing, the cost of a flow 18.2 is always at least its potential function value 18.3. The hypothesis ensures that the cost of a flow is at most gamma times its potential function value. The theorem follows by writing C of f is less than or equals to gamma times phi of f, which is less than or equals to alpha times phi of f star, the optimal flow of GRC, which is less than or equals to gamma times C of f of star, with the second inequality following from proposition 18.11. And theorem 18.16 implies that the price of anarchy of selfish routing is large only in networks with highly nonlinear cost functions. For example, if C is a polynomial function with degree at most p and non-negative coefficients, then x times c of x is less than or equals to p plus 1 times the integrate from 0 to x of c of y dy for all x which is greater than or equals to 0. Theorem 18.16 then shows that the price of anarchy in non-atomic instances with such cost functions is at most linear in P. Corollary 18.17 Potential function bound for polynomials. If GRC is a non-atomic instance with cost functions, that polynomials with non-negative coefficients and a degree at most p, then the price of anarchy of GRC is at most p plus 1. This upper bound is nearly matched by example 18.3, although the upper and the lower bounds differ by roughly a long p multiplicative factor. Exercise 18.1, we close this gap using a different and important proof technique, which is driven by variational inequalities. We first formalize a natural lower bound on the price of anarchy based on P-Gauss-like examples. Definition 18.18 P-Gauss bound. Let C be a non-empty set of cost functions. The P-Gauss bound alpha of C for C, such a non-empty set of cost function is alpha of C is equals to superior for all little c in this C. the non-empty set of cost function within the subperiod of x and r pairs, which also all of them are greater than or equals to 0 of the term alpha times c of r divided by x times c of x plus r minus x times c of r prime, with the understanding that 0 divided by 0 is equals to 1. This is a special definition. The point of the P-Gal bound is that it lower bounds the price of anarchy in instances with cost functions in C. Proposition 18.19. Let C be a set of cost functions that contains all of the constant cost functions. Then the price of anarchy in non-atomic instances with cost functions in C can be arbitrarily close to alpha of C. Proof: fix a choice of C in C and XR which are greater than or equals to 0. We can complete the proof by exhibiting a selfish routing network with cost functions in C and a price of anarchy at least C of R times R divided by the combinations of C of X times X plus C R minus X times C of R. And since C is non-decreasing, this expression is at most 1 if X is greater than or equals to R. We can therefore assume that X is less than R. So let G be a two-vertex, two-edge network as in figure 18.1. Give the lower edge the cost function C1 of y equals to C of y, and the upper edge that the constant cost function C2 of y is equals to C of r. By assumption, both of these cost functions lie in C. Set the traffic ratio to R. Routing all of the traffic on the lower edge yields an equilibrium flow with cost C of R times R. Routing X units of traffic on the lower edge and R minus X units of traffic on the upper edge gives a feasible flow with cost C of X times X plus R minus X times C of R. The price of anarchy in this instance is thus at least C of R times R divided by the cost in the denominator, C of X times X plus R minus X times C of R, as desired. While proposition 18.19 assumes that the set C includes all of the constant cost functions, its conclusion holds whenever C is inhomogeneous, in the sense that C of 0 is greater than 0 for some little c in the C set. Exercise 18.5. We next show that even though the P-Gal bound is based only on P-Gal-like examples, it is also an upper bound on the price of anarchy in general multi-commodity flow networks. The proof requires the following variational inequality characterization of equilibrium flows. Proposition 18.20. Variational inequality characterization. Let F be a feasible flow for the non-atomic instance GRC. The flow F is an equilibrium flow if and only if sigma of C of Fe times Fe, where the sigma summing for all edges is little e in capital E, which is less than or equals to, again, the sigma summing for all edges is little e in capital E of the term C of Fe times Fe star for every flow F star feasible for GRC. Okay, so the proof is fix F and define the function HF on the set of feasible flows by HF of F star, which is equals to doubling summation, where the outer summation summing for all the index I starting from 1 to k, and the inner summation summing for all p in pi. The set of paths of the term Cp of F times Fp star, which is, if we combine the doubling summation, will be the summing for all edges E in E of the term Ce of Fe times Fe star. So the same reversal of sums used to prove the equivalence of 18.1 and 18.2 shows that these two definitions of H of F star agree. The value of h f of f star denotes the cost of a flow f star after the cost function of each edge E has been changed to the constant function everywhere equal to CE of FE. By the second definition of HF, the proposition is equivalent to the assertion that a flow F is an equilibrium flow if and only if it minimizes HF dot over all feasible flows. Now examining the first definition of HF shows that a flow F star minimizes HF if and only if, for every commodity I, FP star greater than 0, only for paths P that minimize CP of F over all SITI paths. Since the flow F satisfies this condition, if and only if it is an equilibrium flow, the proof is complete. We now show that the P-Gauss bound is tight. Theorem 18.21 Tightness of the P-Gauss bound. Let C be a set of constant functions and alpha of C the P-Gauss bound for C. If GRC is a non-atomic instance with constant functions in C, then the price of anarchy of GRC is at most alpha of C. Prove that F star and F be optimal and equilibrium flows, respectively, for a non-atomic instance GRC with constant functions in the set C. The theorem follows by writing the following. C of F star is equals to sigma summing for all edges E and E of the term C of Fe star times Fe star. And that means which is greater than or equals to 1 over alpha of C of the term sigma summing for all edges E and E of the term C of Fe times Fe plus sigma, again summing for all edges of the term Fe star minus Fe times C of Fe, which is greater than or equals to C of F divided by alpha of C, where the first inequality follows from definition 18.18 applied to each edge E with x equals to Fe star and r equals to Fe, and the second inequality follows from proposition 18.20. Now proposition 18.19 and theorem 18.21 show that for essentially every fixed restriction on the allowable cost functions, the price of anarchy is maximized by P-Gauss-like examples, determining the largest possible price of anarchy in P-Gauss-like examples, i.e. the P-Gauss band, is a tractable problem in many cases. For example, it is precisely 4/3 when C is the set of Fi cost functions, exercise 18.6, and more generally, is a 1 minus P times P plus 1 to the term minus of P plus 1 divided by P. Then such kind of 1 minus term then go to the inverse minus 1 exponent, which is approximately asymptotically about P divided by ln P when C is the set of polynomials with degree at most P and non-negative coefficients. In these cases, the maximum price of anarchy among all multi-commodity instances is achieved by the instances in examples 17.1 and 18.3. The P-Gauss bound is also known for several other classes of cost functions. See section 18.6 for references. Remark 18.22 bounds on Brace's paradox. Brace's paradox, example 18.4, shows that adding edges to a network can increase the cost of its equilibrium flow. Since the equilibrium flow in the original network is a candidate for the optimal flow in the second network, the ratio between the costs of the new and original equilibrium flows is a lower bound on the price of anarchy in the latter network. On the other hand, theorem 18.21 and exercise 18.6 show that the price of anarchy is at most 4/3 in every network with Fi cost functions. Thus, adding edges to a network with Fi cost functions cannot increase the cost of its equilibrium flow by more than 4/3 factor. And example 18.4 is therefore a worst-case manifestation of Bayes' paradox in networks with FI cost functions. Similar bounds also apply to the physical analogues of Bayes' paradox that are described in section 18.6. Atomic selfish routing, the price of anarchy. We now consider atomic selfish routing games. We again obtain tight bounds on the price of anarchy, at least for polynomial cost functions, but the discrete nature of atomic instances complicates the analysis. We first note that the potential function method, which gave non-trivial bounds on the price of anarchy for non-atomic instances, theorem 18.16, cannot be used for atomic instances. The difficulty stems from the non-uniqueness of equilibrium flows in atomic instances. Example 18.6. Recall that a bound on the price of anarchy is a guarantee that all equilibrium flows of an instance are nearly optimal. Reviewing the proof of theorem 18.16, we observe that the potential function method argues about only one equilibrium flow, the one with minimal potential function value. As a result, the potential function method is directly useful only for bounding the price of stability rather than the price of anarchy. While these two quantities coincide in non-atomic selfish routing games, they are generally different in atomic ones. See section 18.6 for results on the price of stability in atomic selfish routing games. We instead rely on proof techniques that are partially inspired by the variational inequality of proposition 18.20. This inequality expresses the fact that equilibrium flows route all traffic on shortest paths with respect to the induced edge cost. We derive a similar, if more complicated condition for atomic instance. To keep the proofs as transparent as possible, we focus on atomic instances with the affine cost functions. And recall from theorem 18.15 that every such instance admits at least one equilibrium flow. The analysis can also be extended to other cost functions and other equilibrium concepts. See remark 18.26 and section 18.6 for more details. Our goal is the following theorem. Theorem 18.23, the price of anarchy in Fi atomic instance. If GRC is an atomic instance with Fi cost function, then the price of anarchy of GRC is at most 3 plus the square root of 5 divided by 2, which is approximately around 2.618. A variant of the AAE example, example 18.6, shows that the upper bound in theorem 18.23 is the best possible if different players can control different amounts of flow, exercise 18.2a. If all the players control the same amount of flow, then a variant of the following proof gives an improved upper bound of 5 divided by 2, which matches the lower bound furnished by the AAE example, exercise 18.7. We build up to theorem 18.23 in a sequence of steps. We begin with a lemma that follows immediately from the definition of an equilibrium flow. Lemma 18.24, equilibrium condition. Let GRC be an atomic instance in which each edge E has an Fi cost function, C of x equals to AE of x, AE times x plus BE with the constants AE and BE, which are greater than or equals to 0. Let F and F star be equilibrium and optimal flows respectively. For GRC, let player I use the path PI in F and the path PI star in F star. Then, sigma summing for all edges in PI of the term AE times FE plus BE, which is less than or equals to sigma summing for all edges in PI star of the term AE times FE plus RI times then plus BE. So our second step is to combine the inequalities of lemma 18.24, one per player, to relate the cost of an arbitrary equilibrium flow to that of an optimal flow. Lemma 18.25, equilibrium inequality, with the same assumptions and notation as in lemma 18.24. C of f is less than or equals to C of f star plus sigma summing for all edges in E of AE times FE times FE star. And proof: for each player I, multiply the inequality 18.8 by Ri, summing up the resulting k inequalities. We obtain C of f, which is less than or equals to sigma summing for all index I from 1 to k of the term Ri of the term sigma of E in Pi star of the term AE times the summations of FE plus Ri. Then, after the sigma plus BE, which is less than or equals to sigma, again summing for all k paths of Ri of the term sigma summing for all E in Pi star of the term AE of FE plus FE star plus BE, which is again becomes 1 sigma summing for all edges E in E, little e in capital E over the term FE star times the following term AE times FE plus FE star. Then after the multiplication, we plus BE, where the inequality follows by reversing the order of summation, since the final expression equals the right-hand side of 18.9. The proof is complete. To complete the proof of theorem 18.23, we upbound the magnitude of the error term in 18.9 relative to the cost of the equilibrium and optimal flows. Proof of theorem 18.23. Let F and F star denote equilibrium and optimal flows respectively for the atomic instance GRC. Assume that HE has the cost function C of x, which is equals to AE of x plus BE, for A and B both are greater than or equals to 0. Apply the Cauchy-Schwarz inequality to the vectors. The set little e in capital E of the term square root of AE times FE, and again the set of all indexes little e in capital E of the set of the term square root of AE times FE star to obtain the following. Sigma summing for all edges of the term AE times FE star is less than or equals to the square root of the sigma summing for all edges of the term AE times FE square, again times the square root of the sigma summing for all edges of the term AE times FE star to the square, which is less than or equals to the square root of C of f times the square root of C of f star. Combining this with the equilibrium inequality 18.9, dividing through by C of f star, and rearranging gives C of f divided by C of f star minus 1, which is less than or equals to the square root of C of f divided by C of f star. So squaring both sides and solving the corresponding quadratic inequality, x squared minus 3x plus 1, which is less than or equals to 0, we find that C of f divided by C of f star, which is less than or equals to 3 plus square root of 5 divided by 2, which is approximately 2.618, as claimed. Theorem 18.23 can be extended to atomic instances with cost functions that are polynomials with non-negative coefficients and degree at most a parameter p, and however, the upper bound on the price of anarchy increases with p roughly in proportion to the exponential function p to the p, much faster than in non-atomic instances. This exponential dependence is not an artifact of the above proof approach, as nearly matching lower bounds on the price of anarchy are known. Section 18.6. Remark 18.26. Strictly speaking, the price of anarchy is not always defined in general atomic instances where equilibrium flows need not exist. Example 18.7. Nevertheless, theorem 18.23 has been extended to atomic instances with polynomial cost functions in 3 different ways. First, when such an instance does admit at least one equilibrium flow, then all such flows have cost at most p to the big O of p times that of an optimal flow. Second, by Nash's theorem, chapters 1 and 2, every such instance admits a mixed strategy, Nash equilibrium, and the expected cost of every such equilibrium is at most p to the big O of p times that of an optimal flow. Finally, similar upper bounds have been provided and proved for single equilibria, an equilibrium concept that always exists in finite games and is motivated by convergence issues.